Everyone, our topic today is directed graphs. It's a very important topic because we use it in a lot of applications. Let's start from introduction. So what is directed graph or D-graph? The direct graph is a graph that is made up of set of vertices connected by edges, where the edges have a direction associated with them. For example, here is a direct graph. Here, numbers are vertices, and connection between them are edges. Each edge have a connection. It's the main difference between undirected graph and directed graph. So each vertices have an out degree and in degree. For example, in 0, we have 1 out degree, 2 out degree, and 1 and 2 in degree. So as I said before, we use directed graph in a lot of applications. For example, here, road network. Our vertices are intersection, 1, 2, and 3, and edge, one-way street, like that. Next, our Uber taxi graph. Here, vertex are taxi pickup, 1, 2, 3, like that, and edge are taxi ride. So also we use a combinational circuit. For example, vertices are logical gate and edge are wire. So here we have a problem. For example, ST path. Is there a path between from S to T? Shortest ST path. What's the shortest path from S to T? Directed cycle. Is there a directed cycle in the graph? Topological sort and another one. So let's look at the graph API. Here we have a dgraph int v, our constructor, which create an empty dgraph with v vertices. Next is dgraph in create a dgraph from input stream. Next is void at edge, which have in attributes int v and int w, and so on. Let's look at example. Here our txt. We have some rules that, for example, here we have 13 vertices and we write it in our txt. 13 vertices, we write 1, 2, 3, 4, 5, etc. And 22 edges. Here we have 22 edges. So, for example, if you look at here, 4 and 2. Here we have 4 and 2. It's our connection between these vertices. So here are part of code, which output here. So we create a graph from our input stream, like this, and put to for loop, and just output it. So next we have a indexes array of list. For example, 0. In 0 we have 1 and 5. Here 5 and 1. Next is, for example, 7. In 7 we have 6 and 9, and etc. Next is the graph representation. Here we have agency list representation. For example, a list of edges, agency matrix, and agency list. Difference between them that here there takes different specs. For example, list of edges takes E, edges, agency matrix takes vertex in square, agency list takes E plus V. As you can see, here are agency lists, E plus V. We have V and E connection between them. So like that. Agency matrix, we will see it in the next example. And what is the difference between undirected graph and directed graph? In undirected graph, we have this part of code. This is our constructor. It's very similar in dgraph. In edge, in undirected graph, we don't have an edge, so we add 2 edges from V to W and to W from V. In dgraph, we just delete this part of code because we don't have a 2 directions from V to W or W to V. For example, like that, from 6 to 0. Where in undirected graph, we put from 0 to 6 and from 6 to 0, and like that.
Okay, about the directed graph search. There is a main problem of finding all reachable vertices from S along a directed graph. There is a problem. So we have 2 algorithms to find all these reachable points. The first one, as you know, it's direct depth first search. Depth first search, it's a digraph algorithm. So why we use it DFS in undirected graph, because undirected graph is a digraph with edges in both directions. So how DFS works? We visit the first vertex V as visited, and I recursively visit all unmarked vertices W pointing from V. There is a demo. So as you see, if we start here from 0, we go to 1, and we mark O1 as visited, and then we mark 0, and we go to 5, we go to 4, and etc. There is we have marked array and the H2 array. H2 means from which vertex it came from. For example, for 5 it's 0, because to 5 we came from 0. So there is a Java implementations of DFS for undirected graph. As I said before, DFS is a algorithm for directed graph, so the code is as you see is the same. There is no difference of the first search algorithm for undirected and the directed graph. So DFS applications, it's a reachability application, a program control flow analysis. It's a block of instructions which should run in the order. So by using DFS we can find that got elimination. It's a finding and removing unreachable code, and the infinite loop detection, where if there is exit is unreachable. So here a vertex is our block of instructions, and the edge is a jump from one program to another program. And the next one is mark sweep garbage collector. It's here for garbage collector we have lots of algorithms. One of them is mark sweep. So here we find accessible objects, and here vertex is an object and the edge is a reference, and we find reachable objects, of course. Here's a second algorithm for finding reachable points is, as you know, BFS. BFS is a digraph algorithm too, for as DFS, because undirected graph is a directed graph with edges in both directions. So how BFS works? Put a vertex as its starting vertex onto our FIFA queue, and the mark S as visited. Repeat until queue is empty. Remove the last recently added vertex V for each unmarked vertex pointing from V added to queue, and the mark as visited. BFS running time of BFS, it's E plus V. E is a number of edges, and the V it's a number of vertices. For example, here we firstly add to our queue 0, and we look for 1 and 2. Then we remove from our queue 0, and we check if there is a adjacency list of 1, and if there is no vertices pointing from 1 which is not marketed, we just remove the queue from our queue 1, and etc. Here's an example of this one. And the application of BFS, it's one of the applications of BFS, it's a multiple source shortest path. How we find multiple source shortest path? As we just here we should use as a source not only one vertex, but all of these vertices. So when we initialize Q, we just add all these vertices 1, 7, and 10 in this example, and run BFS, and it will give us multiple shortest paths. So BFS is also used in web crawling. Web crawling to find all connected websites to the root website. Why do not we use GFS? Because GFS goes cheaper and it do not show us the closest website to our root. GFS, it goes, I'm sorry. And why not to use there is a question, why not use GFS? Because GFS, it goes deeper and it finds us first, it gives us the longest. Why not use GFS? Because GFS goes deeper and it doesn't give us the closest websites to our root website. So there is a Java implementation of the web crawler. We use Q for the website crawler and S as a market websites. And there is a root and so on. And there is a there is a difference between BFS crawl and GFS crawl. BFS crawl gives the closest websites, as I said before, and GFS, it goes deeper, and the closest ones returns as last. So that's all.
So now we talk about the topological sorting and the digraph processing applications that doesn't quite have a parallel with the under record graphs. And it's a very general model that is very widely used. And here's a simple example of called precedence scheduling. So the idea is that you've got a set of tasks that have to be completed, but there is a precedence constraints, and you want to know in what order should you schedule this task. So you might think of this as like courses in university curriculum. So as a model, we will use vertices will be the task, and the edges will be the precedence constraints. And all this say there is an edge from 3 to 6 means you have to take introduction to computer science before take advanced programming. And so there is all these sorts of constraints in the graph, and so what you want to, it's called a feasible schedule. So that's just order in which you can take the linear order, which you can take the courses one after the other, then it respects the precedence. So that corresponds to drawing the graph such that all edges point to upwards. And this model is used to study manufacturing processes and many other applications. So that's a topological sorting problem. So first thing is topological sort works on DAG, a so-called DAG. That's a digraph that has no cycles. If you have cycles, there is no way that you are going to able to solve the problem. In fact, your simple graph processing problem is just to find out if graph has cycle. We will talk about later. First of all, we will talk how to find, how to do is find a way to redraw DAG so that all edges point upwards and give a bottom to top order 2. So that's all edges pointing upwards. That's called the topological order of the graph, and that will give in this case an order which maybe you could take the courses or perform the manufacturing process or whatever else. So that's a problem. So how are we going to solve it? We will going to use DFS. In fact, one of the lessons for particularly for digraph processing is DFS is going to provide a way to solve it, and it might be hard to find different way. So let's look at them a topological sort, and all is just run DFS, but there is a particular point which we want to take a vertex out or get the order, and that's called reverse DFS post order. So let's look at how it's work. So we had to just run DFS the same as before, but we're not keeping track of anything except the vertex that we're done with. So vertex 0, we have to check the places that you can get to from 0. It's 1, 2, and the 5. So we check first 1. 1 is unmarked, so we are going to mark it and recursively visit 1. So we do that, we have to check for. So we do that, and we have to check for, and 4 again is unmarked, so we will recurse. But now both of edges to 4 in, so there is nowhere to go from 4. So we're done with 4. When we are done with 4, we output it actually put in stack. So that's order, the order in which we're done with the vertices. That's called post order. So now once we are done with 4, now we are done with 1. There is nowhere else to go. So we put on the post order, and now we are back to 0. And get from 0. So here's 2, and get 2 from 2. And it's unmarked, so we visit it. So we put on post order and go back to 0. And then we go to 5. Unmarked, so we visit it. So then we check 2, which is unmarked, so nothing to do. And then we are done with 5. So now we have to check all other vertices in the graph, or have to find some other place, and so we just check the vertices in the order. Next one that we find that's unmarked is 3. So to visit 3, we have to check 2, 4, and 5. 5 and 6, and the 2, 4, and 5 already marked, so nothing to do. And the 6 is unmarked, so we go to visit 6. When we visit 6, now 0 and 4 already marked. So there is nothing to do, and we are done with 6. And finally, we are done with 3. We are done with the vertex. We put it out the post order, or if we put on the stack, then we get a reverse post order, and that it turns out is the answer that we need. So let's back. So the code is very simple, but we will have to look at little more carefully to be convinced that it works. So the first search, but we have an additional data structure, which is a stack of integers, which is a vertex in reverse post order. So the constructor just creates the stack, and then the only thing we have to change it to DFS is when we are done with the vertex. Before exiting, we put that vertex on the post order, and then the client simply gets a stack returned, and that's iterable. That's iterable. Iterating through that will give a vertex and the reverse TFS post order, which is the top logical sorted order. So if there is a directed cycle, you can so if there is a directed cycle, you can have a topological order. If there is a no directed cycle, then we just found it. So one thing you might want is given a digraph, find a directed cycle, and how we are going to do that. You are going to use TFS, and that's a simple algorithm that you might want to think about, and it's a few lines in the book. So precedence scheduling is an excellent example of the use search directed graph. Um, and this cycle of length 1, of course, that requires itself and as request, and this is just example of very widely used computation. It really has many applications. So for example, Java compiler actually does cycle detection. If you have a class A extends B and another one B extends C and another one C extends A, that's going to create a problem. Class hierarchical not supposed to have a cycle, and it's actually the Java compiler will actually give an error message saying there is cycle inheritance. You are not allowed to do that. So there's a many applications that involve essentially a digraph and aren't supposed to have a cycle. Also, another example of is Microsoft Excel. So if you do a cycle reference like this in Excel, which a big spreadsheet you could image might happen, that's an error. And it's actually got a circular reference toolbar that will help you figure out what you do in that case. So cycle detection and the topological sorting, important application at depth for search and the digraphs. So also there is a one another thing about the topological sort is a question about uniqueness of topological order. If topological sort has a property that all pairs on consecutive vertices in the sorted order are connected by edges, then the edges from directed Hamilton paths in the DAG. If Hamilton paths exists, the topological sort order is unique. So it means that no other order respects the edges of the path.
Let's move to the strong components. Strong components, vertices V and W are strong connected if there's a both directed path from V or to W and directed path from W to V. And we also say that a directed graph is strongly connected if there is a path between all pairs of vertices. So a strongly connected component of a directed graph is a maximal strongly connected subgraph. For example, as you can see, there one strongly connected, 2, 3, 4, 5. 5 strongly connected components, as you can see. And we can see that from 6 we can go to the 8, and from 8 we can go to the backward to 6. So for example, here we from 9 we can go to the 11 and then to the 12, then again to the 9. So we can easily say that there are strongly connected components. Here we can see connected components versus strongly connected components. V and the W are connected if there's a path between V and W. So here you can see just connected components. They're just connected, but the difference between them, the strongly connected, they can both connected from V to W and from W to V. So let's look at some applications. We can see ecological food webs. So in food web graph, you can see that vertex are species, and edge from producer to consumer. Then you can see that mosquito fox can eat mosquito, and it's like that. So subset of species with common energy flow. In strong comment application also we can see that software models. Software model dependency graph, vertex is a software model, vertex age from model to dependency. We talked about the definition about strong connect components and some application. Let's move to the how to find this. We can find all strongly connected components in O time V plus E time using Kaszara algorithm. Big O V plus E. Following detailed Kaszara algorithm, we see further. So let's move to the Kaszara algorithm and find how it works. So first we should create an empty stack as you can see here. So source vertex is equal to 0. So let's start, and we do DFS traversal of graph in DFS traversal. After calling recursive DFS for adjacent vertices of a vertex, push the vertex to the stack. So we go to the 0, we see the direction, go to the 1, see the direction, go to the 2, also again see the direction, go to the 3. So, and here we finally visit all 2 and 0 and 2, and let's put in the stack. So we put 3 in our stack, and let's go further. Our recursive call, it's again go to the 2, then he see also one direction to the 4 and to 5 with this 6, and here he stops because there is no more ways to go further. So and this will go to the stack, we put it in the stack, goes back, also put 5 in the stack, so we also see there is no direction, go to the 4, we also see the 4 and we put it in the stack, push it in the stack, go back to the 2, and etc. We will see that all directions we put it in the stack. So we'll after all this, we'll reverse direction of all arcs to obtain the transpose of the graph. So let's start reverse. So we do a transpose here. In the below you see the transpose of the graph. So then one by one pop a vertex from S while S is not empty. Let's pop a vertex B, V, take V as a source and do DFS call on V. The DFS starting from V prints strongly connected component of V. So let's start to 7. We pop it, then you can see there is no direction and there's only one strong connected component. Then pop 8. You can see also there is no strongly connected component. It pop only one element. Third element, it will pop 0, 3, 2, 1. As you can see, from 0 to you can go to 3, to 1, 2, and to 1, and backward to 0. As you can see, all these are strongly connected components. So let's move to the 4. 4 can go to the 6. 6 can go to the 5, and backwardly go to the 4. So you see all visited connected components. So and at the back you can see that visited all we visited 8 at first, then as we visited 7, then 8, then 0, and all we like that we finished all this. So stack is now empty, we should terminate all. So we, like this, we'll find our strongly connected components, first one, second, third, and fourth. It will go one by one, track it one by one by reversed order. So thank you for the attention and good luck.